So we are given the ALU decomposition of A, and here we are asked to find the orthogonal basis of the four fundamental subspaces and also write the keyword decomposition. So just to recall, the four fundamental subspaces are: one is the column space, which is denoted like this. The second is the row space. Row space is denoted like this. Then we have the null space. Denoted like this, and then we have the left null space. Left null space is denoted like this. So column space is basically the subspace that is spanned by all the columns of A. So suppose we have, say I am writing the columns of A like this: A1, A2, say A3. I am writing up to this. Then I want to, the column space of A will be any linear combination, say x1 times or let me write here alpha 1 times A1 plus alpha 2 times A2 plus alpha 3 times A3. Any linear combination will be the column space. So if we want to find the basis of this column space, so before that I can write this summation like this: A1, A2, A3 to alpha 1, alpha 2, alpha 3. See, we can take this number and multiply with this column. So like that we have written this summation, this linear combination in this matrix form. So column space, if this matrix is A and say I am calling this X, so column space is, so I can write column space as Y such that AX equals to Y. So this is the column space of A. Now similarly for A transpose, I can write the similar analogy, that I will take the columns of A transpose and do that. So that I can write it as Y such that A transpose X equal to Y. Similarly, and now null space is all those X for which AX is 0. Null space of A is all those X such that AX gives 0. So null space is X such that AX is 0, and null space of A transpose can be written as, instead of A we need to write A transpose, basically AX such that X transpose A X equal to 0. Now let us find the dimension or the parent vector space of which this is a subspace of. See, A is a dimension, say A is of M cross N, then Y is basically M cross 1. So this is a subspace of Rm. Then here this is N, this A transpose will be N cross M, so Y is N cross 1, and this row space will be a subspace of Rn. So in null space, here A is M cross N, so X will be N cross 1, and this will be the subspace of Rn, and here A transpose will be N cross M and X is M cross 1, and this will be the subspace of Rn. So I have basically wrote down the which subspace is. And one more interesting property is that the column space of A, any element belonging to the column space of A, is orthogonal to the element belonging to the null space of A transpose. See, both are having the same number of elements, Rm, both are M vectors, and I am claiming that they are orthogonal. And one more thing that is true, that column space of A transpose is orthogonal to the null space of A. So column space of A is orthogonal to the null space of A transpose, and column space of A transpose is orthogonal to the null space of A. You can check that in this case both are M vectors, and in this case both are N vectors. So the dimension means dimension of the vectors matches. Now let me prove why this is true. It's very simple to prove. Say I am taking X belongs to the column space of A and Y belongs to the null space of A transpose. So if X belongs to the column space of A, then by definition I can write that there exists Z such that I can write Az equal to X, right? And since Y belongs to the null space of A transpose, then I can write that A transpose Y equal to 0. Now what is X transpose here from here? X transpose I can write as X transpose equal to Z transpose into A transpose. What is X transpose into Y? Equal to Z transpose into A transpose Y, and A transpose Y is 0, so this is 0, implies X is orthogonal to Y. So now I am proceeding with the solution. I have just given an overview of what the 4 fundamental subspaces was, and now if we want to find the basis of these 4 fundamental subspaces, say I am finding for the column space. I am starting with this column space one. So for the column space we can claim like this, that basically I want to find the basis of the column space of A, right? So if I write A as say like this, A1, A2, A3, I want to find the basis. So to find the basis of the column space, say I take a general combination alpha 1 x A1 plus alpha 2 A2 plus alpha 3 A3 equal to 0. Now I want to eliminate all the dependent parameters, like all the columns that depend on it. So suppose means when I multiply this with this alpha 1, alpha 2, alpha 3, and then I equate it to 0. To find the basis, what I need to do? To find the basis, basically I need to do that, I need to eliminate all the dependent columns. So all the dependent columns I need to eliminate. Say alpha 2 not equal to 0. So if alpha 2 is not equal to 0, then this column is a dependent column. So this column can be expressed as a linear combination of the other two columns. So I need to eliminate that. Now if I perform the same analogy with U, say I am writing U as U1, U2, U3, and I again take the combination alpha 1 U1 plus alpha 2 U2 plus alpha 3 U3 equal to 0. See here also the same coefficient, means if alpha 2 is not equal to 0, then by similar logic this U2 can be represented as a linear combination of U1 and U3. So the point I am trying to make is, to find the basis of the column space of A, we can find the pivot columns in the echelon form of the matrix. So if this is my echelon form, so this is my echelon form, what I am doing is this is my echelon form. Now what we need to do, we need to identify the pivot columns. So here we can draw a line like this, and this column here and this column here, these are the pivot columns. I claim that any other column I can represent as a linear combination of these two columns. Say I want to represent this column as a linear combination, then I can just multiply it by 2. This column if I multiply it by 2, I can get this one. And say I want to represent this, then first what I will do, I will make this coefficient, I will multiply it by 2. Then what is the residual? If I multiply it by 2, it is coming 6. I need to subtract 2, then from this I will subtract 2. So using only these two columns I can make all other columns. So these are my pivot columns of U. Now what will be my pivot columns for these indices? I claim that here the for null spaces, for column spaces, this alpha 2, you can see that when we know which column makes trouble, means which column is independent here, we can redirect to that same index column in the original matrix. So we know that here if I label it like this 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, so I need to go to the second and fourth column of A. Now see 1, 2, 3, 4, 5, so this column here and this column here forms the basis of the column space. So I can write that column space of A equal to span of these two columns. What was that? 1, 1, 0 and 3, 4, 1. 3, 4, 1. Now to make it say orthogonal, I want to make these columns orthogonal. So for that, what I need to do, I need to perform scheme orthonormalization. So first let me make this unit vector. If I want to make this unit vector, what it will be, 1 by root 2 to 1 1 0. Now I need to convert this matrix. So what I will do, I will remove the component that is along this vector, along this unit vector. So what I will do, I will take the dot product. So this is a vector B and this is vector A. So I will do dot product B dot A into A B. So I'll basically do this. So I will remove the component that is along that vector. So what is 3 4 1 dot product with A cap? So 1 by root 2 1 by root 2 0, and I need to multiply this again with 1 by root 2 1 by root 2 0. So what is the dot product here? Here the dot product will be 3 plus 4 7 by root 2 into 1 by root 2 7 by 2 into 1 1 0. So this will be the dot product. Now I need to subtract that through 3 4 1 minus 7 by 2 1 by 2 0. So this is coming 3 minus 6 minus half. So this is coming 7 by 2 half 1. Now you can check that this and this are the dot product is coming 0. So it's cool here. And now what we need to do, let me write it in simple terms here. I can write it as minus 1 1 2. So means I will basically make it a unit vector. So minus 1 1 2 and 4 1 by root 6 1 by root 6. So this is basically a unit vector now. Minus 1 1 2 4 plus 1 5 plus 1 6 6. So I am writing the results in this side. Column space of A. So I got here two vectors, 1 by root 2 1 by root 2 0, 1 by root 2 1 by root 2 0, and minus 1 by root 6 1 by root 6 2 by root 6. Now column space is done. As you can see that what is the dimension of this subspace? It is 2, which is equal to the number of pivots of the rank. Here the rank was 2 here because we had two pivots, and so R is 2, and the number of elements in the dimension of the column space is equal to the rank, and the dimension of the row space is also equal to the rank because row rank is equal to common rank. I am coming to that. So column space is done. Now row space. To find the row space, we need to find the column space of. We can basically do this due to row transformations, means elementary row operations. The rows subspace is not getting changed. So what I am doing in elementary row operation, why we are getting lower triangular matrix? In lower triangular matrix is basically a manifestation of elementary row operations. Elementary row operations, when represented in matrix form, becomes the lower triangular matrix. Now what we are doing, say this is one row R1, R2, R3. So when I do R2 equal to R2 plus 2 R1, so I am not changing the base, I am not changing the span of the, I am not changing the span of the row space, because I am just taking the linear combination. So my span is still the same, and since my span is still the same, when I identify the non-zero rows in the echelon form, that are basically my row space. So here I don't need to do anything, since when I am again explaining that when I am performing elementary row operations, say I am doing R2 equal to R2 plus 2 R1, I am not changing the span of this set. Initially my set was R1 R2 R3, now it is R1 plus R2 plus 2 R1 R1 R3. So my span has not changed. I can do that. I can if I have a set UV, I can make it a set alpha U plus beta V, comma V. So it is valid. I can add a linear combination to that. My span is not getting affected. So now when I identify the non-zero rows here, see here this row is completely 0, so I can eliminate this, and these are my non-zero rows, and then I can claim that this will be my pivots, and so the row space will be simply this. the row space will be 0 1 2 3 0 1 2 3 4 and 0 0 0 1 2. Now the only thing that I need to do is to make this orthogonal. So to make this orthogonal, I can start with any one. Say I start with this. Now what will be the magnitude of this? Magnitude of this will be, let me calculate. One by root 30 times 0 1 2 3 4. So this is one vector in the row space of A. So one vector I got as 0 1 by root 30, 2 by root 30, 3 by root 30, 4 by root. So this is one vector. Now I just need to make this orthogonal. So what I will do, I will basically take the dot product and subtract that 0 0 0 1 2 minus, if I take the dot product, 1 by 30 into the dot product will be 0 0 0, sorry, 0 1 2 3 4, 0 1 2 3 4, and the dot product is 3 plus 8 11. So it is coming 0 minus 11 by 30 minus 22 by 30 minus 3 by 30 So I can basically write it as 0 minus 11 minus 22 minus 3 is 16, and it will be the magnitude 121 plus 1 by root over 870. So just basically I told that how we can do that. So again the dimension of the row space is equal to the rank, which is equal to the dimension of the column space. So in every case, the row space, the column space dimension was R, the row space dimension is also R. Now the null space dimension will be n minus R, and the left null space dimension will be m minus R. Now I am saying how we can find the null space. To find the null space, we need to find x such that Ax is 0. Now I claim that when Ax is 0, that times this Ux is also 0. See, I am multiplying x both sides. If I multiply x both sides, when Ax is 0, that at the same time Ux is also 0. So I can basically solve for Ux equal to 0. That is my means, because solving for this is easier. Now how to solve for Ux equal to 0 is, say I am taking the systematic way, 0 1 2 3 4, 0 0 0 1 2, 0 0 0 0 0. Now it can be x1, x2, x3, x4, x5. Now I want to make it 0. Now see, right in the row echelon form, identify the pivot columns. So this is the pivot column and this is the pivot column. Now corresponding to this pivot columns, we will define something as pivot variables. So pivot variables will be these columns corresponding, this is the pivot variable, and these columns corresponding 0 1 2 3 4. So this is the pivot variables, and all these except pivot variables, whatever we have, this is our free variable. This, all these are free variables. Now what we have to do is systematically put every free variable 1 and the other free variable 0 at a time. Say I am putting x1 0, x3 and x1 as 1 and x3 and x5 as 0. Now I need to find the value of this pivot variable. Consider this equation. This equation is x4 plus 2 x5 is 0. See, x5 is 0, so x4 also has to be 0. And this equation, these 3 are 0, so this one also has to be 0. So this is one vector by putting x1 as 1. Now I will put x3 as 1 and all other free variables as 0. Now similarly here this will be x5 is 0, so x4 will be 0. And what will be the value of x2? x2's value we can find from this equation. x2 is equal to minus 2x3. All others are 0, so minus 2. So this is one more vector. Now we need to put x5 as 1 and the others are 0. So when I put x5 as 1, x4 is minus 2. x4 I got as minus 2, and if I put that x2 minus plus 3x4, all others are 0. No, plus 4x5 equal to 0. We are basically doing back substitution. So x2 is equal to minus 3 into x4 is minus 2 minus 4 into 1. So it is 6 minus 4, which is 2. So this is one more vector. Now we basically need to orthogonalize this. So if I write the null space of A, the first vector is 1 2 3 4 5. So this is the same issue with that. Now check with this, the dot product is 0, so we don't need to do anything with this also. What is the magnitude here? Basically root 5. 4 plus 1 5, 1 by root 5 0, minus 2 1 0 0. Now check with this vector. Here this vector's dot product is not 1, its dot product is 0 with this, but its dot product is non-zero with this vector. So since its dot product is non-zero with this vector, now we need to change this vector. So what will be this value after changing? 0 minus 2 1 minus 1 by 5, and what is the dot product here? Minus 4 minus 4. So this times 0 minus 2 1 0 0. So this is coming here 0 so it is basically what? 0 2 4 minus 10 5. 0 2 4 minus 10 5 and 4 plus 16 5. So the other vector is 1 by root over 145 into 0 2 4 minus 10 5. And now see what is the dimension of the null space here. I claim that it will be n minus r. Here the n value was 5, 5 minus 2 3. Here the dimension is 3, so it is matching. Now the last thing, what is the left null space of A? So for that we need to solve A transpose x equal to 0. Now A transpose x, here we need to convert A transpose to its echelon form and then apply the similar logic. So I am basically stating that if I write A transpose, it will be like this: 2 2 0 3 4 1 4 6 2. Now I will convert this to echelon form again. Now I am basically saying the answer because you can do this, it's pretty easy. So 1 1 0 0 1 1, and the all other columns will be 0 here. x1 x2 x3. Now here see, this is the pivot column and this is the pivot column. So corresponding pivot variables are this and this. This is a free variable. I will put x3 as 1. When I put x3 as 1, x2 will be minus 1 and x1 will be 1. So this is my vector and only one vector. So not much big deal. 1 by root 3 into 1 minus 1 1. Notice the dimension here 1 and what it should be m minus r. So 3 minus 2 1. So our results are matching. Now the last thing, that how to construct the QR decomposition. So in the QR decomposition what we do is, so A equal to QR, here Q is a orthogonal matrix and R we write as the right triangular matrix. So how to construct Q? So Q will be basically that we are taking the column space vectors, orthogonal vectors here, and the left null space. So column space and left null space. First we'll place the column space and then we'll place the left null space. So if I want to write the Q, see I have the column space here. So Q will be 1 by root 2 0 minus 1 by root 6 1 by root 6 2 by root 6, and now I'll put the left null space which is 1 by root 3 minus 1 by root 3 1 by root 3. So I got my Q. And R how to calculate, I can, Q is an orthogonal matrix, you can easily check. This is the column space of A and this is the left null space. And to check whether, see, these two will be orthogonal because the column space of A is orthogonal to the null space of A transpose. I have already shown, and these vectors individually are also orthogonal because I have performed Gram-Schmidt orthogonalization here. So overall Q is an orthogonal matrix, and as Q is an orthogonal matrix we can write R as Q transpose into A. So to find R you can do this, I have already found, so I am directly writing the answer. R will come 0 root 2 2 root 2 7 by root 2 5 root 2 0 0 0 3 by root 2 6 3 by root 6 3 by root 6 0 0 0 0. So you can see that it is the right triangular matrix. Now one thing that I want to show, that here I need to show that why this element is 0. Say why this element is 0. So to prove why this element is 0, why, when we are getting this element, when we are multiplying this with the first column of A. So the first column of A belongs to the column space of A, and the null space of A is orthogonal to the column space of A. Null space of A transpose is orthogonal to the column space of A. That's why this element is coming as 0. Similarly, you can show that using this calculation you can show that without performing the calculation if you want to show. So this was our QR decomposition. Yes, of A.